Our next speaker is Emma Tosch from UMass. Emma?
Thank you, Jan. And this is PlanAlyzer, assessing threats to the validity of online field experiments. And this is work with Eytan Bakshy of Facebook and some folks at UMass, Emery and Eliot, who many of you know, and David Jensen. So the first thing you might be asking about this talk, if you're unfamiliar with the domain, is what are online field experiments? So suppose you run a website, for example, the failing New York Times. You'd like to see if you can't increase some subscription metric by testing out different messages on your subscription button. Now, suppose your website is written in JavaScript, and suppose that there are two variables you want to bind to. Message, which refers to the text of the subscription button, and an object that tracks what you want to store for later analysis. Also suppose that somewhere else in the code you're recording clicks. So you implement this test in JavaScript like so. You flip a coin every time a user visits, and some small percentage of the time you randomly assign that visitor to one of two messages. Then you store what message was used, and some of you who are sitting in the audience may recognize this simple experiment as an A/B test. So now that you've written an online field experiment, what do you do with it? So you want to analyze the results in service of some question: does my treatment, which here corresponds to the message text, have an effect on the outcome of interest, which we've alluded to being a function of clicks? So let's consider a possible outcome of interest and the associated procedure for estimating it. So we want to know whether there was a difference in the click rate between people who saw message A and the people who saw message B. This is an instance of a well-known estimator of causal effect, known as average treatment effect, also referred to as ATE. So in this case, the two treatments we consider are these two variants of the message, and this is often written in a way that abstracts over the outcome variable, just referring to it as Y. So statisticians, you'll see, often use this notation, and we'll see it again later in the talk. The important part here is that ATE can only be applied to certain pairs of treatments, which are referred to as contrasts. However, there is a problem with this setup. Our outcome of interest is in terms of people who clicked on the button, but our code isn't tracking people. We don't know how many individuals have clicked on that button, and in the worst case, the data could be coming from the same person, and in the best case, we might have one data point per person. So this isn't a problem because there are DSLs for experimentation that we can leverage. Popular choice is Facebook's PlanOut. So PlanOut is a framework that PlanOut has a framework that backs it, and it supports sampling, which we had previously been doing in this outer coin flip, but don't actually need anymore. PlanOut also manages concurrently running experiments, which is a very important feature and rationale for why people choose to use PlanOut in the first place, but it's actually tangential to the concerns of this talk. More important to us is the fact that PlanOut manages data recording, so we no longer need to track manually which message the users received. And then we have the DSL itself, whose features we'll get to in a moment, but for now, know that it looks like JavaScript with some named arguments, and its purpose is to map units to treatments. So knowing this, we might like to update this script expressing this experiment a bit more compactly, and while we're at it, we might decide to make it a little more targeted by only running the experiment on paying customers rather than, for example, pesky graduate students like me who have a subscription through their university. So the ability to iterate on design that you see here is critically important to the process of experimentation. And well, we'll see throughout this talk that the examples that we're using are pretty straightforward and pretty simple, but this workflow encapsulates a representative use case for PlanOut where the deployed versions of experiments can be quite a bit more complex than our running example. So critically, we must be able to iterate over the design. So the key here is that the mapping between treatments and subjects, in order to accurately estimate the average treatment effect, has to be unbiased. So how does PlanOut express this mapping? Well, first we'll introduce some of the domain-specific features of PlanOut that aid in the mapping, and then we'll address the heart of the issue. How can we know whether this mapping is unbiased, and how do we know whether our analyses are consistent with that mapping? So PlanOut contains built-in pseudo-random functions that are seeded with some experiment-specific, and there are more than these two, these are just for this example, but they're seeded with some experiment-specific data, including the unit of randomization. So that must always be specified explicitly and can actually be an arbitrary expression. A critical feature of any language that one writes for experimentation is a mechanism for specifying what data gets recorded. And PlanOut overloads the return operator so that if its argument evaluates to false, then the data defined along that path is not actually recorded. And no return statement is implicitly a return true. And finally, while not strictly necessary for an experimentation DSL, PlanOut permits calls to external functions. So now that we've covered the language features that allow us to express the mapping, let's get to the heart of the talk where we have to figure out how to determine whether the mapping of units to treatments is unbiased, allowing us to fairly estimate ATE, for example, from the script we wrote earlier. So where are the places where we could possibly go wrong? Well, we have the design phase, which in this context corresponds to a PlanOut script. And then we have the execution phase, where subjects are actually exposed to treatments. And then finally, we have the analysis phase, where we compute estimators of causal effects, such as ATE. It's possible that somewhere between the design and execution phases, something causes the mapping of units to treatments to fail. For example, there's a bug in the rendering of a web page on a particular mobile phone, and the type of phone would then be correlated with both treatment and outcome, rendering any estimate of effect inaccurate. We also expect there to be a set of analyses that are consistent with the original design of the experiment. However, if there's nothing to link these two, then it's possible for the experiment to desynchronize with the analyses, which also introduces bias. So also because running experiments is very costly, we restrict ourselves to those that don't involve user data. This means we won't be looking at the execution phase here, since it requires knowing the actual treatments being mapped. We can, however, use static program analysis to identify some threats to internal validity of these PlanOut scripts, automating some components of the statistical analysis phase by generating critical data such as contrasts and conditioning sets. So to this end, we've built a tool called PlanAlyzer that handles both of these tasks. So what does PlanAlyzer actually do? Well, first it checks for these threats to validity of PlanOut programs, which are actually based on well-known problems in the experimental design literature. And in particular, how they manifest in PlanOut code. If it doesn't detect these threats, then PlanAlyzer will generate contrasts and conditioning sets for eligible experiments. We've already discussed contrasts and have seen an example, and we'll discuss conditioning sets later in this talk, but the important thing to know right now is that they're a kind of constraint on the contrasts. So how does PlanAlyzer perform these analyses? Well, it runs path-sensitive analysis using special variable labels that capture important concepts that are necessary for us to reason about experimental design over a path-based representation and data dependence graph, and then it uses an SMT solver to aid in contrast generation. So now let's discuss some of these threats to validity. First, we have recording non-random treatments. So suppose we decide to change our code so we have a default message for visitors whom we can't upsell. So we modify the code by adding that default message, but in doing so, we delete that return statement. The problem here is that we never want to mix deterministically assigned treatment variables with randomly assigned ones. And this is the sort of thing that PlanAlyzer will find. Fortunately, we can fix this problem by inserting a return statement. Great, we did it. So now consider another threat where we don't actually record the values that we're conditioning on. So suppose you want a different message A for each population. You modify the code like so. So notice here, there's no return statement. We've just changed one of the treatments. The problem here is that if that datum that we're conditioning on, so the one that appears in the conditional statement, isn't recorded, isn't saved in a named variable in this context, if it isn't saved in a named variable, then it doesn't end up being recorded. So this is only an error when this variable is an unrecorded confounder or a cause of both treatment and outcome. So if you have an incredible short-term memory, you may be wondering about the original plan-out version of this script, of this experiment, and what we do about branching on that unrecorded coin flip. Well, in this case, the random operator cannot cause outcome, and so by virtue of being randomly defined in the script. And so this is actually okay, and PlanAlyzer finds the first case and ignores the second. Fortunately, we can fix this problem by storing the potential confounder in a variable that we can condition on. So we modify the code like so. And once again, great, we did it. And then we also want to consider turning off randomization as one of the threats to validity. So this can actually happen for a variety of reasons. But we're going to look at one because it's kind of a weird concept in programming languages, this idea of units of randomization and the fact that we can have arbitrary expressions in it. So suppose that you also want to vary the button color in your experiment. You have no idea how units work, and you write something like this here. So recall that assignment is pseudo-random. Then you have two problems. First is that color has only 3 values, so it's possible that they could all end up in the same bucket, causing us to never see one of the messages. The second problem is that because color is only pseudo-randomly assigned, each color will only map to a single message. So for example, we'll never see both red and give the times and red and play the crossword. So PlanAlyzer finds this. Unfortunately, we actually have no idea what the author intended to do here, and the fix is not immediately obvious. So now that we've covered some threats to validity, let's take a look at contrast generation. So let's return to the original example where we were just selecting between 2 messages, and recall that this was the expression that we had for the contrast. So now let's see what this looks like for subpopulations, where we're restricting ourselves to people that we're actually able to upsell. So here are our contrasts. So you might be wondering why this is the same as the previous code block. Well, in this particular case, we have only one recorded path through the program, and so the branch will only take on one value, so it isn't really a conditioning set. So this is a statistical concept known as a frame, and what's important about it is that the size of this potential confounder allows us to determine whether it should be included in the conditioning set, and this is a simple example wherein the programmer used an SMT solver. So now let's consider an example where we had different messages. Here we don't want to combine the results from both branches, so we have to do what's called subgroup analysis, where we partition our average treatment effect on the basis of the unsellable variable. This is known as the conditional average treatment effect, or CATE. So great, we've summarized some of the threats to validity and challenges in generating contrasts. Now, how do we evaluate what we've done? Well, to evaluate the identification of threats to validity, we need a representative corpus containing buggy scripts. And to evaluate contrast generation, we need a representative corpus of scripts and contrasts. So in service of this, we acquired a private corpus of plan-out scripts from Facebook, which we partitioned into 3 corpora. So corpus A contained high-quality scripts that were vetted, deployed, and analyzed for ATE, and we were also given contrast for a subset of these scripts. So because of this, corpus A is a very good choice for evaluating contrast generation. In corpus B, we had high-quality experiments that were vetted and deployed, but they were not analyzed for ATE, but they were possibly analyzed for CATE. And so we hope this corpus would be a good choice for evaluating conditioning sets. And finally, corpus C contains experiments that were never deployed, but could potentially be useful for identifying threats to validity in the wild. So how well does PlanAlyzer do at finding the threats to validity in the corpus? We have a complete explanation of the threats, errors, and false positives in the paper, but the high-level view is that the corpora are actually not that useful for assessing PlanAlyzer on threats, since the most common errors that we observed involve mixing testing code, where, for example, a particular user or group of users are deterministically assigned treatments. And then also, people would actually use PlanOut for things that were not experimentation. So that said, this is not actually that surprising since we kind of expected that most PlanOut users at Facebook are experts in experimental design, or that they have access to someone who has expertise in experimental design, and also they gave us this corpus, so it's probably going to be pretty good. Yeah. So what do we do in the face of this? So since the corpora aren't great for identifying experiments, we will instead mutate some scripts in order to tax our system. So first, let's consider some features of corpus A. Our median and average lines of code are quite a bit longer than the examples we've been looking at, and the number of paths in the intermediate representation is a good proxy for the number of branches in the original program. So we defined 8 mutation types, 5 of which would raise errors depending on context. We then randomly selected 50 scripts and mutated them according to their AST rather than, for example, sampling randomly from the possible mutations. And finally, we ran PlanAlyzer on these 50 scripts and manually verified the output. The precision and recall of this mutation were quite high, indicating that PlanAlyzer works as we expected it to. And so finally, we need to evaluate how well PlanAlyzer does on the correct identification of contrasts. We had 95 experiments from Corpus A that had gold standard data, and we manually verified the output, finding equivalent contrasts for 78 scripts. The remaining 17 we had are currently outside the scope of our tools. So for 3 of them, they had sort of garbled data in them. We're not really sure what was going on there. But for the remaining 14, those were all cases where the set of treatments we had was actually very large, but people were interested in essentially marginalizing over it. We do not produce we produce the full set of treatments, and we don't do the marginalization because actually creating all of these things is very expensive. So we're okay with that. Okay, so that's the overview of what we've done. I do want to address this because this is something that it's really hard to sort of live in the world we are in today and not think about these things. I am not an employee of Facebook. I cannot speak for Facebook. I'm not here to, it's not my job to defend Facebook, but I also know that there are really thoughtful people there. I've really appreciated the support I've gotten from people there on this project. And I also know that, what's actually going on in the world right now is so much more complicated than what gets reported in the news. That said, I also know that a lot of how we think about digital institutions is really broken. And I see a lot of people who react to this by saying it is unethical to even experiment at all. And it's really hard to work in this area and be like, am I part of the problem? So I don't have expertise in these things. I really encourage you to check out people who do. I strongly agree with this blog post on how to think about experimentation. And I would encourage everyone to inform themselves and think about the opportunity cost of not experimenting. Also, so then what do we do about this? They say that, so I'm graduating. It always feels really vulgar to be like, hey guys, I'm graduating. So I'm graduating. I also think this area is very important, but also very complicated. And we should all consider working on it. I would love to consider working on it, but also I don't know what I'm going to do in my personal future. And so I very much encourage you to consider this domain. There are people working out there to try to make fair systems for experimentation, and I think that there are a lot of folks here at Uppsala who would have a lot to offer, and strongly encourage you to take a look at that and make the world a better place. So I would like to thank everyone, my collaborators and their support over the years, my lab mates, and the reviewers who gave awesome detailed reviews. So thanks everyone.
Questions? Anyone?
I have a ton of backup slides, so.
There's a question here, don't worry.
So you mentioned briefly about the marginalization as something that your tool didn't find, and then you said it was computationally intensive. Can you just say a little bit more about that? Is that something that a future tool could maybe do, or is that just something you'd never want to do?
Yeah, so the output that you see here with the average treatment effect, the average and then the Y, that thing. So those are all pairwise comparisons, and they're very, very obviously very expensive to compute. So you can ask for that output from the tool, but it also actually produces CSVs with the idea that you would like load this into a database. So there might be a smart way to do it. I don't know yet.
Maybe I just missed it, but I don't really know what ATE and KATE are. So could you?
AT is average treatment effect, and KATE is conditional average treatment effect. So in the A/B test, when we compare between A and B, that's a very simple example of average treatment effect. When we look at the sum of these, like when we average over all the outcomes for each of them and then subtract them.
All right. Any more questions? Well, if not, let's thank Emma.